Okay, so for the next 3 days, we're going to work on what is called U substitution or UDU substitution, not do. Okay. This is basically our way of doing the chain rule in reverse, but very specific things have to happen inside of our integral for us to be able to use this. Okay. Also, this strategy, there are lots of different types of problems that we're going to see. Okay, we're spending 3 days on it because of that. The only way that you are going to get the hang of UDU substitution and recognizing when you need to use it is by doing practice problems. Okay, the more problems you are exposed to, the easier it's going to be for you to recognize when it's going to work and when it will not. Okay, so it is vital that you do your homework these next 3 days. Okay, luckily you have all weekend to do the homework assignment for tonight. All right, so we know if we take the derivative of a composition, we have to use the chain rule. So F composed with G, when we take the derivative, we get F prime of G times G prime, right? So using our antiderivative, let's think backwards strategy, right? If we have the integral of F prime of G times G prime, then we know that antiderivative will be F composed with G plus some constant C. Right? That makes sense? Okay, if we have the composition, we have its derivative, we take the antiderivative, we get back to the same place. Now, we do not call this the chain rule when we're talking about antiderivatives because we don't always get exactly what you see up there. Sometimes we have to tweak it a little bit, okay? But working backwards with the chain rule, this is what we call U substitution, okay? Sometimes I'll just call it substitution, but we're going to use a U as our variable to use for substitution. The best way I could describe to look for an opportunity to use this technique is when we have some sort of a composition of two functions. Okay. If we have a composition times another function, like you see here, we have a composition times another function. That should give us kind of a warning flag. Maybe we can use U substitution. Now, since, if we have an integral that looks like this, our G is inside and then it's times a G prime, okay? When we do the U substitution, and I'll show you what I mean by U substitution, we're basically going to pick a piece of this integral and set it equal to U, and then rewrite our integral in terms of U. Okay, so what we're going to try to do is we're going to try to let the inner function be equal to U in our composition. Once we get through an example, I can point out a little bit more of why we want that inner function to be U. Okay, on the next slide, I'm going to give you step by step what I want you to do for U substitution, okay? And then we'll actually go through those steps with a problem, okay? We're going to start out very simple, and as we go through today, Monday, Tuesday, we'll basically get more complicated with our examples. So this is what you are going to do. First of all, you are going to choose a u. Something inside of your integral, you're going to say u equals whatever that is. Okay? Typically, it's going to be what is inside a function. Once we have written u equals g of x, then we are going to take the derivative and we're going to write it as a differential. You remember where we had like y dy equals 5dx, okay, right? The dy and the dx were split apart in differentials, okay? Now we're doing u substitution because we can't use the power rule or any trig rules to get our antiderivative. So the point of u substitution is to take our integral and write it in terms of u so we can use our basic rules. So our next step is going to be to rewrite everything in terms of u. Whatever g of x equals, that is going to become a u. You're also going to have a value for dx, so you're going to substitute dx with something that's going to have a du. Okay, so eventually you're going to get an integral with u's and du. At that point, hopefully we can take the antiderivative, and so you're going to do that with respect to u. You're actually going to take the antiderivative. But since we started with a function that was in terms of x, when you get your answer, you're going to want to go back and replace all of your u's with g of x, since those two were equal. So like I said, we're going to do a couple very straightforward examples so you can see how this lays out. And then as we go through the day, we'll tweak it just a little bit. Okay? So, first example, write it down. Okay, so do you notice how we have a composition times another function? We have something inside of that, something to the 50th power, right? And then we have it multiplied by another function. So this is our composition times another function, okay? Now, I made this a ridiculous exponent because how many of us want to take x squared plus 1 to the 50th power? And then multiply it by 2x, and then take the antiderivative. Cool? No. Nobody wants to do that, okay? That would take way too much time and effort, okay? But that, until u substitution, that would be the only way we could do this problem, would be to multiply it all out so we could use the power rule, okay? But now we have u substitution. So what we can do is our inner function x squared plus 1, we can let that equal u. Then we're going to take the derivative, and remember we're going to do so like we did in our differential section. So du equals 2x dx. Okay. Is that bringing back some memories from differentials? Okay, so now we're going to go back to our integral. We know that x squared plus 1 is the same thing as u. So we are going to replace x squared plus 1 with u. So we have u to the 50th power. And then we have this 2x dx. What do we know about 2x dx? It equals du. So we can replace 2x dx with du. And now we have a really nice integral, don't we? Okay. U to the 50th power. If we take the antiderivative of u to the 50th power, we get u to the 51st power times 1 over 51 plus c. Now, our original integral, what was the variable inside? X. What do I expect your answer to be in terms of? X. So we're going to go back up to here. We know u is x squared plus 1. So our answer is really 1 over 51 times x squared plus 1 to the 51st power plus c. Any questions on any part of that process? Pretty slick, right? Let's try another one. I know, they keep sagging. Okay, if you have another spot that they would look nice, you let me know, okay, Cole?
Above the door.
You can always put them on the bottom.
Come on that board over there.
That board over there? Okay, thank you.
Well,
Can I leave them for today?
what?
Can I leave them for today?
Yeah. As long as you pull it, you know.
Okay, so we have an issue here because we have a product inside of our antiderivative. I told you that you cannot take the antiderivative of a product, okay? But with u substitution, hopefully we can rewrite it so that we can take the antiderivative, okay? What would be considered the composition in this integral? Cosine of x cubed, right? X cubed is inside of cosine. So what we can do is we can let u be equal to x cubed, and conveniently du would be equal to the derivative of x cubed is 3x squared dx. See how that's convenient for us? So then what we can do, since u equals x cubed, we can rewrite cosine of x cubed as cosine of u. And then we have this 3x squared times dx. Well, 3x squared times dx we can replace with du. So now we have just a simple integral cosine of u du. Grant, what's the antiderivative of cosine? Okay. Ah, that's what I was looking for. I knew you'd get there. Okay, so Logan, how would I want you to rewrite this for your final answer?
Sine of x cubed
plus C.
Very good. Replace u with whatever you used for the substitution. All right. I would like you to work on this integral, okay? Without me walking through each step, I would like to see how far you can get with this integral. Do you have a composition times a function? Yes. Yes, you do. This is the perfect candidate to try u substitution. Bless you. Josh, what is your u?
Oh, so 2x left for it.
Okay. Good. Connor, what was your next step?
Take the derivative of u.
Okay, so can you read it off to me?
Du equals 8x cubed dx.
Okay, for those of you who may be struggling with that notation, think of this, okay? You are right. If we take the derivative with respect to x, then du dx equals 2x to the fourth. And so all we're really doing is taking that dx to the other side. Okay, that's what we did in our differentials chapter. So if this helps you get to here, you can add that step in. Okay, that's what we did in our differentials section. But we have the knowledge to just go straight to here. If you wish, that's what you told me, right? Okay, so then, how do we rewrite our integral, Larry?
Secant squared u du.
Aaron, what's the antiderivative for secant squared?
Put tangent.
So tangent of u plus c. So your final answer should be tangent of, was it 4x? What was it?
X to the 4.
Plus c.
Okay, sorry, it was secant squared u.
That's not going to be a thing. Okay, so far, when we have chosen a u, du has been exactly what we needed it to be, right? Okay. What happens if it isn't exactly what du equals? Okay.
Show us.
Of course, I'm going to show you. Write down this example. Okay, we do have a composition times another function. Right now, but before today, we would have no way to take this antiderivative. Since there is a product, we know we cannot take the antiderivative of a product without doing something, okay? So U substitution gives us an opportunity to maybe rewrite it, okay? Trevor, what would you set U equal to?
The 5x cubed plus 4.
Do you agree with Trevor? Is that what you would do?
Yes.
Okay, that is the function inside of another one, so that's the one that we want to try. Okay, now if U is 5x cubed plus 4, then du would be 15x squared dx. Okay. Now the good news, obviously we have a dx. Do we have an x squared? We do have an x squared, right? We have x squared dx right here. But we do not have that 15, do we? Okay? So what we can do is we can take this and we can divide the 15 over. Okay? So we can write that 1/15 du equals x squared dx. And now we have something to substitute in for x squared dx. Okay? So if you're off by just like that coefficient, divide that coefficient over so you have exactly what is inside of your integral. Okay? So now we can take this integral, okay? Obviously we're going to have the square root of u. All right? And then x squared dx is the same thing as 1/15 du. X cubed plus 4, we substituted u. X squared dx, we substituted 1/15 du. Okay, now this doesn't look very pretty. We can rewrite it. My suggestion would be to take that coefficient, throw it on the outside of the integral, just save it till the end, and then we can write this as u to the 1/2 du because then it's easier for our power rule. So now when we take the antiderivative, we have that coefficient that's going to stay there, times u to the 1/2 becomes u to the 3/2 times 2/3 plus c. So we have 2/45 u to the 3/2 plus c. And of course, I do not want you to leave it in terms of u. I want you to change it back. U is u is 5x cubed plus 4. So we're going to write this as 5x cubed plus 4. There's our final. So the issue here was our du was just differing by a coefficient of what we needed to, so we just divided that coefficient over to do our substitution. All right, I think we have one more example. Okay, and then I want to talk about a couple things. We do have a product which is not good for antiderivatives. We can't take the antiderivative right now because there is a product. But luckily we have a composition times a product, so we can try to see if U substitution will work. If we are going to try U substitution, Austin, what would you choose for U?
X to the sixth.
Which means du would be 6x to the 5th dx. Does that put us on the right track? Are we going to be able to make this work? We should be able to make this work, okay? We know that x to the 6th we can replace with u. Well, we have this x to the 5th dx, which we have right here. So in order to be able to replace that, what are we going to need to do with this 6 right here? We're going to need to divide it over. Okay? So x to the 5th dx really equals 1/6 du. So now we can take our integral. We obviously have the sine of u, but then x to the 5th dx, we have that right here. We're going to replace it with 1/6 du. So how I would prefer you to write it is 1/6 sine of u du. Now we have something very simple to take the antiderivative of. Okay. Sandy, what's the antiderivative of sine?
Negative cosine.
So we have negative 1/6 cosine of u plus c. So as our final answer, we're going to have negative 1/6 cosine of x to the 6th plus c. What do you think? Kind of a neat trick, right? Okay. Now, so far every example that I have given you has worked out just fine. Right? Now, let's talk about a couple problems that maybe won't be as nice. I think yesterday in your, I don't really remember exactly what it was, but you had an integral that looked like this, right? It was a binomial squared. That's really all I remember about it. Okay? Now, this is a composition, but it's not multiplied by anything, right? So if we try to do a u substitution where 2x squared plus 3 is u, when we find our du to be 4x, we don't have that 4x multiplied anywhere to be able to make that substitution work. So the only way to be able to take this antiderivative would be to multiply that out, so you can use the power rule 3 times. Okay. Here's another one that is not going to work with U substitution. Take a moment and talk to your pod about why U substitution will not work. 1, 2, 3, go. Yeah.
Are you gonna let me divide X out? Or like, no?
Okay, so like divide X over. Where would you put it? Huh? The only thing that we can put on the outside of the integral is a constant. So if this was like 1/2 X, we could put the 1/2 outside. So pod number 4, what did you say?
The X goes into the right power.
Okay, so here we have our composition multiplied to X, but if we let U equal X cubed plus 2, then du is 3x squared dx. We only have an x dx. We don't have an x squared dx. Okay? So there has to be kind of a relationship with that inner function and what's on the outside, right? So since U substitution won't work, what would we have to do? Well, we would have to multiply that out so we could use the power rule 3 times. So U substitution does not solve all of our problems, but it's a way for us to calculate a lot more antiderivatives. Now, your homework, okay, is technically 1 through 25 odd on page 301. I have highlighted problems that are absolutely necessary for you to do, and problems that are highly suggested, highly encouraged that you do on top of those. Okay? Now, we have, what?
2.
10? We have 10 minutes. My watch says 8:43 and we get out of here at 8:53. So what I'd like you to do is open up your book, share if you need to, and at least get, I would say 2 problems, if not 3 finished. I actually want to talk about those first few. So everybody turn to 301 with me. Okay? When you do number 1 and number 3, all they are asking of you is to identify what U would be and then identify what du would equal. Okay? They don't actually, the 1 and 3 are like, hey, set this up, and then 5 through 25 are actually performing the antiderivative.